On October 1st, 1964, a sleek white train departed Tokyo Station at precisely 6 a.m., reaching Osaka, 515 kilometers away, in just 4 hours. This wasn't merely a new train service, it was the world's first dedicated high-speed rail system, and it changed transportation forever. The Shinkansen. In English, we call it the bullet train, a name that captures both its speed and its streamlined, projectile-like design. But in Japan, Shinkansen means new trunk line, a technical term that undersells what this system actually represents, a complete reimagining of rail transport. Since 1964, the Shinkansen has carried over 10 billion passengers. Not a single passenger has died from a train accident in those 6 decades. Average delay time, 18 seconds per train. In some years, the average delay has been under 1 minute, including delays caused by natural disasters. These numbers seem impossible. They're not. Today, the Shinkansen network spans over 3,000 kilometers, connecting Japan's major islands from Hokkaido in the frozen north to Kyushu in the subtropical south. 9 different lines carry nearly 450,000 passengers daily. During peak hours, trains on the busiest route depart Tokyo every 3 minutes. To understand why Japan built this system, you need to understand Japan in the 1950s. The country was rebuilding after World War II. The existing Tokaido railway line, connecting Tokyo and Osaka along Japan's Pacific coast, was overwhelmed. This single corridor carried over 60% of Japan's passenger traffic and 25% of its freight. The narrow-gauge tracks, dating to the 1880s, were at capacity. Japan faced a choice: expand the old system incrementally or build something entirely new. They chose revolution over evolution. The Shinkansen wasn't just faster trains on existing tracks. It required new tracks built to standard gauge, 143.5 centimeters between rails instead of Japan's traditional 106.7 centimeters. It required routes designed for sustained speeds over 200 kilometers per hour, with curves measured in kilometers, not meters. It required abandoning grade crossings entirely, no intersections with roads, no pedestrian crossings, nothing that could block the tracks. Most radically, it required convincing a skeptical public and government to fund what was then the world's most expensive infrastructure project. The initial Tokaido Shinkansen cost 380 billion yen, about 3 trillion yen in today's money, or roughly 20 billion US dollars. Japan's entire national railway was nearly bankrupt. Critics called it a reckless gamble. They were wrong. Within 3 years, the Tokaido Shinkansen was profitable. Within 7 years, it had repaid its construction debt. The bullet train didn't just connect cities. It created economic corridors, transformed regional economies, and proved that high-speed rail could work at scale. This is the story of how Japan built the impossible, why it worked, and how it continues to define the future of rail transport 60 years later. The Shinkansen's origins trace back to 1939, before World War II, when Japanese railway engineers first proposed a high-speed line between Tokyo and Shimonoseki. The plan called for standard gauge tracks and speeds up to 200 kilometers per hour. War interrupted everything. The tunnels begun for that pre-war bullet train sat abandoned for decades. By 1955, Japan's economy was recovering, but its infrastructure was strangled. The Tokaido Main Line carried 60 passenger trains and 52 freight trains daily in each direction, far beyond its designed capacity. Journey times between Tokyo and Osaka had barely improved since the 1930s, still taking nearly 7 hours. Engineers calculated that conventional improvements could reduce this to perhaps 6 hours, but the line would remain hopelessly congested. Shinji Sogo, president of Japanese National Railways, and Hideo Shima, the chief engineer, proposed something audacious: build an entirely separate railway dedicated exclusively to high-speed passenger service. No freight trains, no slow local services, no compromises, just speed. The proposal faced immediate opposition. The World Bank, which Japan consulted for potential financing, rejected the project outright, calling it economically unfeasible. They recommended investing in highways instead, following the American model. Japanese government ministers questioned whether the country could afford such extravagance while still rebuilding from war. But Sogo and Shima had powerful arguments. Japan's geography made highways less efficient than in America. Mountains and rivers required constant tunneling and bridging. Railways could move far more people per unit of energy and land. Most critically, Japan was preparing to host the 1964 Summer Olympics in Tokyo. The world would be watching. What better way to announce Japan's return to the world stage than with a technological marvel? The government approved the project in 1958. Construction began in April 1959. They had 5 years to build 515 kilometers of railway from scratch, including 66 tunnels, totaling 77 kilometers, and 96 bridges, totaling 30 kilometers. Nearly 20% of the route would be either underground or elevated. The engineering challenges were immense. Japan sits on the Pacific Ring of Fire, one of the most seismically active regions on Earth. The tracks had to withstand earthquakes. They also had to handle typhoons, heavy snow in mountain regions, and the intense humidity of Japanese summers. The solution was over-engineering everything. Trackbeds were built on thick, concrete slabs rather than traditional ballast. This provided stability and reduced maintenance, though it cost far more initially. Curves had minimum radii of 2,500 meters. Compare this to conventional railways, which often feature curves of 200 to 400 meters. Such gentle curves allowed sustained high speeds without slowing. Gradients were limited to 20 parts per thousand, or a 2%. Incline. This sounds minor, but it was revolutionary for Japanese railways, which previously climbed mountain passes with gradients up to 6.7%. The new limitation meant extensive tunneling. The Tana Tunnel at nearly 8 kilometers was the longest railway tunnel in Japan when completed. Grade crossings were eliminated entirely. Every road, every pedestrian path, every waterway crossed the Shinkansen either above or below the tracks. This prevented accidents and allowed trains to maintain maximum speed continuously. It also dramatically increased construction costs as bridges and tunnels replaced simple crossings. The trains themselves required new technology. Conventional trains used locomotives that pulled passenger cars. The Shinkansen distributed electric motors throughout the train in multiple cars, a configuration called distributed traction or electric multiple unit. This provided better acceleration, reduced weight on any single axle, and meant a train could continue operating even if one motor failed. The original Series 0 trains, with their distinctive bullet nose shape, consisted of 16 cars and could seat over 2,300 passengers. They weighed 720 tons fully loaded and were designed to cruise at 210 kilometers per hour with a maximum speed of 256 kilometers per hour. Every car except the dining cars had motors. Power came from overhead catenary wires carrying 25,000 volts of alternating current. This was more efficient than the direct current systems used on conventional railways, reducing power losses over long distances. Substations every 50 kilometers provided power to the network. Testing began in 1962 on completed sections. Engineers discovered unexpected problems. At high speeds, pantographs, the arms that connect trains to overhead wires, bounced violently, losing contact and causing sparks. The solution required redesigning both the pantographs and the catenary wire system to maintain stable contact at over 200 kilometers per hour. Aerodynamics created another challenge. When two trains passed each other at combined speeds exceeding 400 kilometers per hour, the air pressure differential could crack windows. Engineers strengthened the car bodies and redesigned window seals to handle the pressure waves. The official opening came on October 1, 1964, 9 days before the Tokyo Olympics began. The first service, the Hikari or Light, completed the Tokyo-Osaka journey in 4 hours exactly, averaging 129 kilometers per hour, including stops. The slower Kodama or Echo service, which stopped at all stations, took 5 hours. The world took notice. Here was a train traveling at speeds that rivaled propeller aircraft, yet carrying over 1,000 passengers in comfort, departing every hour and running on electricity rather than petroleum. The Shinkansen proved that the future of transportation didn't have to look like America's highways. There was another path. The technical innovations that make the Shinkansen possible go far beyond simply building straight tracks and fast trains. The system represents an integrated approach to high-speed rail where every component, from the track bed to the train nose to the signaling system, works together as a unified whole. Start with the tracks themselves. Standard gauge Shinkansen tracks are built on continuous welded rail, with individual rail sections welded together to eliminate gaps. Conventional railways have small gaps between rail sections to allow for thermal expansion, creating the rhythmic clicking sound trains make. The Shinkansen is silent because there are no gaps. The rails are instead pre-stressed and held by special fasteners that accommodate thermal expansion without breaking the continuous surface. The trackbed sits on a concrete slab rather than crushed stone ballast. This slab track system costs 3 times more than ballast track, but requires far less maintenance and provides superior stability at high speeds. Sensors embedded throughout the slab continuously monitor for settling or movement. The the entire system is designed to remain within 1 millimeter of specification at 300 kilometers per hour. Even minor irregularities become dangerous. Curves are designed using transition spirals that gradually change the radius, allowing trains to enter and exit curves smoothly without sudden lateral forces on passengers. The track is banked or super elevated on curves, tilting the entire roadbed so that the train leans into the turn naturally. The cant, the difference in height between outer and inner rails, is calculated precisely for the design speed of each section. The trains themselves are masterpieces of aerodynamic engineering. Early Shinkansen trains had a rounded nose, but this created problems. When trains entered tunnels at high speed, they compressed the air ahead of them. This compression wave traveled through the tunnel at the speed of sound and exploded out the far end as a sonic boom. Literally, a tunnel boom that could be heard kilometers away and sometimes cracked windows in nearby buildings. The solution was the elongated nose design seen on modern Shinkansen trains. Engineers studied the kingfisher bird, which dives into water at high speed without making a splash. The bird's long, tapered beak parts the water smoothly. Applying this principle, the nose of the Series 500 train stretches 15 meters, nearly 1/10 of the entire train length, creating a gradual transition that reduces the pressure wave by 30%. This biomimicry transformed the nose from a cosmetic feature into critical infrastructure. The train body itself is a semi-monocoque aluminum alloy structure, combining lightweight with high strength. The entire shell acts as a structural element, similar to aircraft fuselages. This construction reduces weight compared to steel while maintaining rigidity. Lower weight means less energy consumption and less wear on tracks. A lighter train also stops faster, critical for safety. Propulsion comes from three-phase alternating current induction motors mounted on the trucks beneath the cars. Modern Shinkansen trains use distributed power, with typically 8 of 16 cars motorized. Each motor produces roughly 300 kilowatts. The system delivers power smoothly through variable frequency drives that precisely control motor speed. During acceleration, the system can draw 10 megawatts, equivalent to powering 10,000 homes. Braking combines multiple systems for redundancy and efficiency. Regenerative braking converts the motors into generators, feeding electricity back into the overhead catenary system. This recovers roughly 15% of the energy used for acceleration. When regenerative braking alone is insufficient, disc brakes on each axle provide additional stopping power. For emergencies, every car has magnetic track brakes, metal shoes that can be pressed directly against the rails, creating tremendous friction. A Shinkansen traveling at 270 kilometers per hour can stop within 4,000 meters using normal braking or within 3,000 meters in emergencies. The pantograph system that transfers power from overhead wires has been refined over 6 decades. Modern pantographs use carbon fiber contact strips that maintain consistent pressure against the catenary wire across a wide range of speeds and conditions. Springs and pneumatic systems adjust the pressure dynamically. At 320 kilometers per hour, the pantograph remains in contact with the wire 99.9% of the time. Any gap longer than a few milliseconds would cause dangerous arcing. Earthquake detection represents perhaps the most critical safety innovation. Japan experiences thousands of earthquakes annually, including many that could derail trains. The Shinkansen deploys a network of seismometers along the entire route and throughout the broader region. When these sensors detect the initial primary waves of an earthquake, which travel faster than the more destructive secondary waves, they trigger automatic emergency braking on all trains within the affected area. The system provides typically 10 to 30 seconds of warning before strong shaking arrives. Trains automatically begin braking, and power to the affected section is cut. This system has prevented derailments in multiple major earthquakes, including the magnitude 6.8 Niigata earthquake in 2004 and the magnitude 9.0 Tohoku earthquake in 2011. In the latter, the most powerful earthquake ever recorded in Japan, 27 Shinkansen trains were operating in the affected area. All stopped safely, though some faced strong shaking while stationary. Not one derailed. Not one passenger was injured. Maintenance follows a philosophy of prevention rather than repair. Every night after the last train, inspection trains examine the entire network using lasers, ultrasound, and cameras to detect microscopic cracks, worn components, or track irregularities. Maintenance crews have a roughly 6-hour window to inspect and repair before the first morning train. Major maintenance happens during longer breaks in service or on backup tracks. Trains themselves undergo inspection every 1,500 kilometers, roughly every 3 days of service. Every component from brake pads to door mechanisms is checked. Every 3 million kilometers, approximately 10 years of service, trains are completely disassembled and rebuilt. The signaling system, called ATC or Automatic Train Control, continuously monitors train position and speed. Rather than relying on line-side signals that drivers must see and obey, the ATC system transmits speed limits directly to the train through the rails. If a train exceeds the permitted speed, brakes automatically engage. Human error cannot cause speeding. This system has been in place since 1964 and has never failed to prevent an overspeed condition. All these systems work together. The smooth tracks allow high speeds. The aerodynamic trains reduce energy consumption. The distributed power provides reliable acceleration. The regenerative braking recovers energy. The earthquake detection prevents disasters. The intensive maintenance ensures reliability. Remove any single element and the entire system degrades. The Shinkansen succeeds because it is a system, not just a collection of fast trains. The original Tokaido Shinkansen proved so successful that expansion became inevitable. Today, 9 separate Shinkansen lines connect Japan's major cities, each designed for specific geographic and economic needs. The Tokaido Shinkansen remains the busiest, carrying over 165 million passengers annually on its 515-kilometer route from Tokyo to Osaka. Trains depart Tokyo Station every few minutes during peak hours, with departures timed to the second. The line serves 17 stations including Yokohama, Nagoya, and Kyoto. The fastest Nozomi services complete the journey in 2 hours and 21 minutes, averaging 220 kilometers per hour, including stops. During its peak year before the pandemic, the Tokaido Shinkansen carried 452,000 passengers daily, making it one of the world's most intensively used railway lines. In 1972, the Sanyo Shinkansen extended the network from Osaka to Fukuoka, adding 644 kilometers and connecting western Honshu with Kyushu Island through an undersea tunnel. This extension brought the total network length to over 1,100 kilometers and connected Japan's 3 largest metropolitan areas, Tokyo, Osaka, and Fukuoka. The Sanyo line passes through Hiroshima and numerous smaller cities, transforming Western Japan's economy by making day trips possible across distances that previously required overnight journeys. The Tohoku Shinkansen opened in 1982, connecting Tokyo with northern Japan. The line now extends 675 kilometers to Shin Aomori at the northern tip of Honshu Island. Unlike the densely populated Tokaido Corridor, the Tohoku line traverses more rural terrain, climbing through mountains and crossing deep valleys. It serves important cities including Sendai, the largest city in northeastern Japan, and numerous smaller cities that gained economic vitality from Shinkansen access. Maximum operating speed on the Tohoku line reaches 320 kilometers per hour on certain sections, making it the fastest regularly scheduled train service in Japan. From Tohoku Shinkansen, several branch lines diverge. The Yamagata Shinkansen branches west at Fukushima, running 148 kilometers to Yamagata and Shinjo. The Akita Shinkansen branches at Morioka, running 127 kilometers to Akita on the Japan Sea coast. These lines use a clever solution to extend Shinkansen service into areas where building dedicated high-speed track would be prohibitively expensive. The branches run on upgraded conventional track re-gauged to standard gauge, allowing Shinkansen trains to continue beyond the main network at reduced speeds. This mini Shinkansen concept provides direct service without transfers, though speeds drop to around 130 kilometers per hour on the branch sections. The Joetsu Shinkansen, completed in 1982 alongside Tohoku, runs 304 kilometers from Tokyo to Niigata on the Japan Sea coast. This route required boring through the Japan Alps, including the 22-kilometer Daishimizu Tunnel, at the time the longest land tunnel in the world. Winter brings heavy snowfall to this region. Some areas receive over 10 meters annually. The trains and tracks incorporate special features to handle snow, including powerful heating elements and enclosed platforms at many stations. The Hokuriku Shinkansen represents one of the most ambitious extensions, connecting Tokyo to Japan's western coast through formidable mountain terrain. The first section opened in 1997 to Nagano, built in time for the 1998 Winter Olympics. Extensions reached Kanazawa in 2015 and Tsuruga in 2024, with the final section to Osaka planned for 2046. The line required exceptional engineering, crossing the Japan Alps through multiple long tunnels and traversing regions with extreme snowfall. The route reduces Tokyo-Kanazawa travel time from over 4 hours by conventional rail to just 2 hours and 28 minutes. The Kyushu Shinkansen connects Fukuoka with Kagoshima at the southern tip of Kyushu Island. The 257-kilometer line opened in 2011 after construction in 2 phases. The route runs through volcanic terrain, passing near Kumamoto and crossing regions affected by volcanic ash from Sakurajima, one of Japan's most active volcanoes. Despite these challenges, trains maintain schedules with the same reliability as other Shinkansen lines. Most recently, the Hokkaido Shinkansen extended the network to Japan's northern island. The line opened to Shin Hakodate Hokuto in 2016 and will eventually reach Sapporo, Hokkaido's capital. The route includes the 54-kilometer Seikan Tunnel connecting Honshu and Hokkaido islands under the Tsugaru Strait. At its deepest point, the tunnel sits 240 meters below the seabed and 140 meters below sea level. When completed in 1988, it was the world's longest tunnel of any kind. The tunnel presents unique challenges for high-speed rail. It was originally built for slower conventional trains, and upgrading it for Shinkansen service while maintaining freight traffic required complex engineering compromises. Shinkansen trains currently travel through the tunnel at reduced speeds of 160 kilometers per hour, though future modifications may allow higher speeds. The Nishi-Kyushu Shinkansen, the newest line, opened in 2022, connecting Takeo Onsen with Nagasaki over 66 kilometers. This isolated section is not yet connected to the main network due to disagreements over the route through Saga Prefecture, creating an unusual situation where passengers must transfer between conventional and Shinkansen trains. Plans exist to eventually create through service to Fukuoka. Together, these lines form a network exceeding 3,000 kilometers, connecting cities from Kagoshima in the subtropical south to Hakodate in the subarctic north. The network serves a population of over 100 million people within 1 hour of a Shinkansen station. Cities along the routes have seen dramatic economic transformations. Property values near stations increased substantially. Businesses relocated to take advantage of rapid access to Tokyo. Tourism flourished as travel times shrank. The network is not complete. Extensions continue. The Hokkaido Shinkansen will reach Sapporo by 2031, adding another 201 kilometers. The Hokuriku Shinkansen extension to Osaka will add hundreds of additional kilometers. The Chuo Shinkansen, using maglev technology, will create an entirely new route between Tokyo and Osaka via Nagoya, reducing the journey to just 67 minutes. Each expansion faces the same challenges that confronted the original Tokaido line: enormous costs, difficult terrain, skeptical politicians, and competing demands for limited resources. Yet each completed section has justified the investment through economic growth, reduced highway congestion, lower carbon emissions compared to air travel, and improved quality of life for residents of connected cities. The Shinkansen network has become essential infrastructure, as critical to modern Japan as its ports and airports. The Shinkansen's safety record stands unmatched in transportation history. Since the first train departed Tokyo in 1964, over 10 billion passengers have traveled on the network. In those 6 decades, spanning more than 60 years of continuous operation, not a single passenger has died due to a train accident. No derailments have caused fatalities. No collisions have occurred. This safety record becomes even more remarkable considering Japan's geographic challenges: frequent earthquakes, typhoons, heavy snow, and volcanic activity. The zero fatality record reflects obsessive attention to every potential failure mode. The earthquake detection system has prevented what could have been catastrophic derailments. The automatic train control system has prevented every possible speeding incident. The intensive maintenance schedule catches problems before they cause failures. The grade-separated tracks eliminate the possibility of collisions with vehicles or pedestrians. Redundant systems ensure that no single failure can cause an accident. Compare this record to other transportation modes. Air travel, often considered the safest form of transport, has a global fatality rate of approximately 0.07 deaths per billion passenger kilometers. The Shinkansen has operated for over 2 trillion passenger kilometers with 0 fatalities, a rate of exactly 0. Highways, the dominant transportation mode in most developed countries, kill over 1.3 million people globally each year. In Japan alone, road accidents kill several thousand people annually. The Shinkansen has killed none. The safety record is not accidental or lucky. It results from systematic engineering that assumes failure is always possible and designs multiple layers of protection. The automatic train control system means human error cannot cause overspeed derailments. The earthquake detection system means seismic events cannot surprise trains at full speed. The intensive maintenance means component failures are detected before they cause accidents. The dedicated tracks mean no external object can obstruct the railway. Beyond safety, the Shinkansen is famous for punctuality that seems impossible to anyone familiar with typical rail systems. The average delay across the entire network is approximately 18 seconds per train. This includes delays from earthquakes, typhoons, mechanical problems, and human factors. During some years, average delays have been under 1 minute. Trains delayed by more than 5 minutes are so rare that they make news when they occur. This punctuality requires extraordinary operational discipline. Every train has a precise schedule measured to the second. Drivers receive continuous updates on their exact position relative to schedule. Dispatch centers monitor every train in real time, making instantaneous adjustments to maintain spacing and timing. Station operations are choreographed with precision. Doors open and close at predetermined times. Cleaning crews have exactly 7 minutes to clean a 16-car train. Passengers know exactly where on the platform each car will stop. The timetable itself is optimized using sophisticated computer algorithms that balance conflicting demands. Trains must be spaced safely apart, but also scheduled densely enough to meet capacity needs. Express trains must pass slower trains without causing delays. Maintenance windows must be accommodated. The resulting timetable is essentially a mathematical proof that every train can reach its destination on time if every operation proceeds as planned. The weak point in this system is external factors that can't be perfectly controlled. Earthquakes cause delays when trains must slow down or stop. Typhoons reduce maximum speeds due to high winds. Heavy snow requires additional caution, yet even these disruptions are managed systematically. Weather forecasts trigger preemptive schedule adjustments. Earthquake protocols get trains moving again as quickly as safety allows. The system is designed to degrade gracefully. Delays are minimized and managed rather than cascading into chaos. Frequency of service on major routes is extraordinary. During peak morning hours, Nozomi trains depart Tokyo Station for Osaka every 6 minutes. Throughout most of the day, headways remain under 10 minutes. This means the Tokaido Shinkansen operates like a metro system stretched across 515 kilometers. Passengers generally don't consult schedules. They simply go to the station knowing a train will depart shortly. This frequency is possible because of train capacity and track design. A single Shinkansen train carries over 1,300 passengers. With trains every 6 minutes, the line can move over 13,000 passengers per hour in each direction, far exceeding the capacity of any highway or airline route. The dedicated tracks and automatic train control system allow safe operation at these close intervals. Station operations deserve special attention. Major Shinkansen stations handle dozens of trains per hour across multiple platforms. Tokyo Station has 5 Shinkansen platforms serving different lines. Shin Osaka Station serves both Tokaido and Sanyo lines. These stations function as precisely timed machines, with trains arriving and departing on opposite sides of the same platform simultaneously. Cleaning crews demonstrate remarkable efficiency. A team of typically 7 to 9 cleaners boards a train the moment passengers disembark. Each cleaner has specific cars assigned. They remove trash, wipe surfaces, adjust seat positions, check seat pockets, and clean bathrooms, all in 7 minutes or less. The process is so refined that cleaning teams have become tourist attractions, with videos of their synchronized movements going viral online. Crew training is exhaustive. Shinkansen drivers undergo years of training before operating trains independently. They must master not just driving technique, but also emergency procedures, detailed knowledge of the route, and protocols for dozens of unusual situations. Conductors receive similarly intensive training. The driver and conductor maintain constant communication, cross-checking each other's actions. Before departure, they perform synchronized gestures, pointing and calling out checks, a technique called shisa kanko that reduces human error by requiring conscious acknowledgement of each action. The Operations Control Center in Tokyo monitors every train in the network using a real-time display showing train positions, speeds, and status. Controllers can communicate instantly with any train crew. They monitor weather, track conditions, power supply, and maintenance activities. The system generates alerts for any deviation from normal parameters. This centralized monitoring allows rapid response to problems and coordination across the entire network. Reserve trains wait at major stations, ready to replace any train with mechanical problems. If a train cannot continue service, passengers transfer to the reserve train within minutes. The delayed train is moved off the main line for repair. Such substitutions happen smoothly enough that many passengers don't realize anything unusual occurred. The operational excellence of the Shinkansen reflects Japanese cultural values of precision, reliability, and respect for passengers' time. Delays are considered failures, not inevitable inconveniences. Punctuality is an obligation, not an aspiration. Safety is absolute, not a calculated risk. These values, combined with rigorous engineering and operational discipline, create a transportation system that seems to defy normal limitations. It works not because of any single innovation, but because every element is designed, maintained, and operated to the highest possible standard. Boarding a Shinkansen reveals why the system has become deeply embedded in Japanese culture. The experience combines efficiency with comfort, technology with tradition, creating something distinctly Japanese that has influenced how millions of people travel. Passengers enter stations through ticket gates that read magnetic tickets or integrated circuit cards with a simple tap. Reserved seats can be purchased from ticket machines or staffed counters, with precise car and seat numbers assigned. The platforms display electronic boards showing exactly where each car will stop. Markings on the platform floor align with train doors, allowing passengers to queue in orderly lines that perfectly match door positions. When the train arrives, exiting passengers disembark first, then waiting passengers board. The process takes roughly 2 minutes per station. Inside, the trains reveal their dual nature, simultaneously utilitarian mass transit and premium travel experience. Ordinary class seats offer 104 centimeters of pitch, more spacious than most airline business class. Seats recline substantially without encroaching on the passenger behind, thanks to a mechanism where the seat bottom slides forward as the back reclines. Each row has power outlets. Overhead racks store luggage. Everything is clean, functional, and well-maintained. Green Car, the first-class equivalent, provides even more space with 116 centimeters of pitch, wider seats, and additional amenities. The cars are quieter and less crowded. Attendants pass through offering beverages and snacks. For business travelers and those willing to pay a premium, Green Car transforms the journey into a mobile office or relaxation space. Grand Class, introduced on some newer trains, elevates luxury further with seats approaching airline first-class standards. The seats are wider, with extensive reclining capability, footrests, and reading lights. Attendants provide full meal service. These cars remain relatively empty compared to ordinary class, offering privacy and quiet for executives and tourists seeking premium experiences. Restrooms on Shinkansen trains showcase Japanese attention to hygiene and comfort. Western-style and Japanese-style toilets are both available. Everything is spotlessly clean, with attendants checking facilities regularly. Newer trains include wheelchair-accessible restrooms and baby-changing stations. The toilets work at high speed without issue, a technical achievement given that conventional train toilets simply drop waste onto the tracks, an approach impossible for trains running through densely populated areas at 300 kilometers per hour. Shinkansen trains use sealed retention tanks, adding weight but ensuring hygiene. Food represents a crucial element of the Shinkansen experience. While trains have basic refreshment carts, the real tradition is ekiben, station bento boxes. Each major station sells distinctive ekiben featuring regional specialties. In Yokohama, it might be shumai dumplings. In Nagoya, miso katsu pork cutlet. In Hiroshima, oyster rice. In Hakata, mentaiko spicy cod roe. Travelers often plan trips partly around which ekiben to try. The ekiben tradition predates the Shinkansen, originating in the Meiji era when train travel was slower and passengers needed substantial meals for long journeys. The Shinkansen reduced journey times dramatically, but ekiben endured as part of the travel ritual. Buying an ekiben before boarding, opening it as the train departs, and eating while watching the landscape blur past has become an integral part of riding the Shinkansen. The boxes themselves are often elaborate, designed to keep food at proper temperatures and present it attractively. Some trains still operate trolley service where attendants push carts through cars selling drinks, snacks, and souvenirs. The attendants bow upon entering and leaving each car, thanking passengers for riding. They navigate the moving train with practiced ease, never spilling or stumbling. This personal service has declined on some routes as vending machines and stations offer more options, but on longer routes the trolley service continues, maintaining a connection to earlier eras of train travel. The cultural impact of the Shinkansen extends far beyond transportation logistics. The trains have become symbols of Japanese technological achievement and national identity. The distinctive white and blue Series 0 trains appeared on postage stamps, currency, and promotional materials. When foreigners think of Japan, the bullet train often features prominently in their mental image, alongside Mount Fuji, cherry blossoms, and Tokyo's neon-lit streets. The Shinkansen enabled new patterns of life. People could live in smaller cities with lower housing costs while commuting to Tokyo for work. This transformed regions like Shizuoka and Gunma, turning agricultural areas into suburban extensions of metropolitan Tokyo. Real estate values near Shinkansen stations increased dramatically, creating economic benefits while also raising concerns about inequality between connected and non-connected areas. Tourism flourished as travel times collapsed. A trip from Tokyo to Kyoto dropped from over 7 hours to barely over 2 hours. What was previously a significant journey requiring careful planning became a casual day trip. Tourists could visit multiple cities in a single trip without exhausting time budgets. This accessibility helped preserve historical sites in smaller cities by making them economically viable tourist destinations. The Shinkansen influenced Japanese business culture. Same-day business trips across the country became routine. Companies could centralize headquarters in Tokyo while maintaining factories and offices elsewhere. Knowing executives could visit remote sites and return the same day. This contributed to Tokyo's continued dominance as a business center while allowing manufacturing to remain distributed across the country. The trains appear throughout Japanese popular culture. Films use the Shinkansen as settings for drama, comedy, and action. Anime features the trains as symbols of speed and modernity. Video games include Shinkansen driving simulators. Children grow up seeing the trains as aspirational technology, inspiring some to become engineers. The trains are simultaneously everyday infrastructure and objects of fascination. Environmental benefits have grown increasingly relevant. A Shinkansen train powered by electricity from relatively clean sources produces far less carbon dioxide per passenger than automobiles or aircraft covering the same route. As Japan works toward carbon neutrality, the Shinkansen represents a model for sustainable long-distance travel. Some newer trains incorporate regenerative braking more extensively, feeding power back into the grid. Solar panels on station roofs provide electricity for lighting and systems. The social experience differs markedly from air or car travel. Passengers can work on laptops with reliable power and smooth ride quality. They can make phone calls in designated areas. They can move around freely, visit restrooms or food cars without restrictions. Groups can sit together and converse. Children can play without disturbing others. The journey itself becomes productive time rather than dead time to endure. This combination of speed, comfort, reliability, safety, and cultural significance has made the Shinkansen indispensable to Japanese society. Over 60 years, it has evolved from an audacious experiment to essential infrastructure that shapes where people live, work, and travel. It demonstrates that public transportation can be simultaneously efficient and pleasant, profitable and beneficial to society, cutting-edge and culturally meaningful. The Shinkansen is not just a train system, it is a testament to what careful engineering, sustained investment, and cultural commitment to excellence can achieve. The Shinkansen's success inspired a global revolution in rail transportation. Before 1964, high-speed rail was theoretical. After the Tokaido Shinkansen proved both technically feasible and economically viable, countries worldwide studied the Japanese model and adapted its principles to their own needs. France launched its TGV program in the 1970s, opening the first line between Paris and Lyon in 1981. The TGV adopted many Shinkansen concepts: dedicated high-speed tracks, distributed power, advanced signaling, while making distinct choices. French trains used articulated bogies where adjacent cars share wheel sets, reducing weight and improving stability. The TGV initially used more concentrated power with locomotives at each end rather than fully distributed motors. Despite these differences, the debt to Japanese engineering was explicit. French engineers studied the Shinkansen extensively before designing their system. Germany followed with its IC trains in the 1990s. Spain built the AVE network connecting Madrid with Barcelona and other cities. Italy developed the Frecciarossa services. South Korea opened the KTX in 2004, using French TGV technology, but clearly inspired by Japan's success. China began building high-speed rail in the 2000s and has since constructed the world's largest network, exceeding 40,000 kilometers. Every system traces conceptual lineage back to the Shinkansen. Japan has actively exported Shinkansen technology and expertise. The most successful example is Taiwan's high-speed rail, which opened in 2007. The 345-kilometer line connecting Taipei and Kaohsiung uses Shinkansen technology throughout. Trains derived from the Series 700, signaling systems, maintenance protocols, and operational procedures all based on Japanese models. Japanese companies provided extensive training and technical support. The result is a system that mirrors the Shinkansen's safety and punctuality records, proving the approach works outside Japan. India represents the most ambitious ongoing export project. Japan is financing and building a 508-kilometer high-speed rail line between Mumbai and Ahmedabad using Shinkansen technology. The project faces enormous challenges: cost overruns, land acquisition difficulties, political complications, and the need to adapt Japanese technology to Indian conditions. Trains will be based on the E5 series, capable of 320 kilometers per hour. The project has been delayed repeatedly, with completion now expected in the late 2020s. If successful, it could open a massive market for Japanese rail technology across India and other developing countries. Other export efforts have struggled. Plans for high-speed rail in the United States using Shinkansen technology have repeatedly failed to materialize. Texas, California, and the Northeast Corridor have all considered Japanese systems, but political opposition, funding challenges, and competing priorities have prevented construction. The United Kingdom studied Shinkansen technology for its high-speed lines but ultimately chose other approaches. These failures reflect less on the technology than on the difficulty of building any new infrastructure in countries without recent experience with major rail projects. The Shinkansen's influence extends beyond direct technology transfer. The system demonstrated that high-speed rail could compete successfully with air travel on routes up to about 1,000 kilometers and with automobiles on shorter routes. This realization shifted transportation planning worldwide. European countries invested heavily in high-speed rail networks that have captured significant market share from airlines. China's high-speed rail has fundamentally altered domestic travel patterns, making trains the dominant mode for intercity travel. Environmental benefits have driven recent interest. Aviation produces significant carbon emissions, particularly on short routes where takeoff and landing consume disproportionate fuel. High-speed rail powered by electricity, especially from renewable sources, offers dramatically lower emissions per passenger. As climate change concerns intensify, the Shinkansen model of electric high-speed rail becomes increasingly attractive compared to kerosene-burning aircraft. Even as the Shinkansen has inspired systems worldwide, Japan continues innovating. The most dramatic development is the Chuo Shinkansen, using magnetic levitation technology rather than steel wheels on rails. Maglev trains levitate above guideway using powerful magnets, eliminating friction and allowing even higher speeds than wheeled trains can achieve. The Chuo Shinkansen will run from Tokyo to Nagoya, about 286 kilometers, with journey times of just 40 minutes compared to 90 minutes on the existing Tokaido Shinkansen. The route will eventually extend to Osaka, creating an alternative to the heavily congested Tokaido line. Trains will operate at 505 kilometers per hour in revenue service, making it the fastest train system in the world. The technology has been tested extensively. Experimental maglev trains have operated on a test track since the 1990s, reaching speeds exceeding 600 kilometers per hour. Construction began in 2014 but has faced significant challenges. The route requires extensive tunneling. About 86% of the line will be underground, including a 25-kilometer section under the Southern Alps, Japan's most formidable mountain range. Environmental concerns about groundwater disruption have slowed progress. Costs have escalated dramatically, now exceeding 9 trillion yen, making it one of the most expensive infrastructure projects in history. The Tokyo-Nagoya section is now expected to open around 2034, with the Nagoya-Osaka section delayed until at least 2045. Critics question whether maglev is necessary. The existing Tokaido Shinkansen, even at over 60 years old, continues operating efficiently. The time savings from maglev are substantial but not revolutionary. 40 minutes instead of 90 minutes to Nagoya. The enormous cost could potentially fund other infrastructure or social programs. Proponents argue that redundancy is essential. If an earthquake severely damages the Tokaido Shinkansen, the entire Tokyo-Osaka corridor would face paralysis. The Chuo Shinkansen provides backup routing and added capacity for one of the world's most economically critical transportation corridors. Beyond maglev, conventional Shinkansen technology continues advancing. The Alpha X is an experimental train testing technologies for the next generation of Shinkansen. It features an extraordinarily long nose, 22 meters, to further reduce tunnel boom effects. Active suspension systems will automatically tilt the train body on curves, allowing higher speeds on existing track. Advanced braking systems aim to reduce stopping distances. Quieter pantographs and improved aerodynamics will reduce noise pollution for communities near tracks. Energy efficiency gains continued attention. Newer trains use lighter materials, more efficient motors, and better aerodynamics to reduce power consumption. Some experimental systems recover energy from braking more effectively or use it to power station facilities. Solar panels on station roofs and alongside tracks contribute to power supplies. The goal is carbon neutrality across the entire network within coming decades. Autonomous operation is being explored. While Shinkansen trains already operate with extensive automation, the automatic train control system handles speed regulation. Human drivers still control starting, stopping, and monitor for problems. Fully autonomous operation could potentially increase capacity by allowing even closer train spacing and reduce labor costs. However, the safety culture prioritizes redundancy, and removing human oversight entirely faces resistance. Any autonomous system would need to demonstrate safety exceeding the current perfect record. The Shinkansen's global influence will likely grow. As more countries seek alternatives to carbon-intensive air and automobile travel, high-speed rail based on principles established by the Shinkansen becomes increasingly attractive. Japanese companies continue offering technology, financing, and expertise to countries developing new systems. The original dream of the Shinkansen, fast, safe, reliable, comfortable train travel that transforms how people live and work, has proven universally appealing. What began as one nation's solution to a transportation crisis has become a model for sustainable mobility worldwide. 60 years after that first train departed Tokyo Station in 1964, the Shinkansen stands as one of the most consequential infrastructure achievements in modern history. Its impact extends far beyond simply moving people quickly between cities. The system fundamentally changed how a nation functions, demonstrating possibilities that seemed impossible and establishing standards that have yet to be matched. The raw numbers tell part of the story. Over 10 billion passengers carried. 0 passenger fatalities from accidents. Average delays measured in seconds. These statistics achieve a level of performance that seems to violate normal rules about complex systems. Most infrastructure degrades over time, becomes less reliable, requires increasing maintenance. The Shinkansen has instead improved continuously, becoming faster, more frequent, more comfortable, and more efficient with each passing decade. But statistics alone miss the deeper transformation. The Shinkansen changed Japanese geography in fundamental ways. Cities that were provincial outposts became prosperous suburbs of Tokyo. Regions separated by mountains and distance became economically integrated. The psychological distance between places collapsed along with travel time. When Tokyo and Osaka went from 7 hours apart to 2 hours apart, they effectively became parts of the same metropolitan region. This integration created economic efficiencies, spread prosperity more evenly, and gave people choices about where to live that would have been impossible in a pre-Shinkansen world. The system preserved Japanese railways at a time when rail was declining globally. In the United States, passenger rail collapsed under competition from automobiles and aircraft. European rail systems survived but struggled with declining ridership and mounting debts. Japan chose differently, investing heavily in a new form of rail that could compete successfully with other modes. That choice saved Japanese national railways from obsolescence and created an asset that continues generating value decades later. The Tokaido Shinkansen alone generates substantial profits that fund maintenance, improvements, and expansion of the broader network. The safety culture established by the Shinkansen offers lessons applicable far beyond railways. The assumption that failure is always possible, the engineering of multiple redundant protections, the intensive maintenance that prevents problems before they occur, the operational discipline that treats every deviation as unacceptable. These principles could improve safety in numerous domains. The zero fatality record proves that extraordinary safety is achievable when organizations commit to it absolutely rather than accepting calculated risks. The Shinkansen demonstrated that public transportation could be desirable rather than merely utilitarian. Many transportation systems worldwide function adequately but inspire no enthusiasm. People use them because they must, not because they want to. The Shinkansen achieved something different, a system that people actively prefer over alternatives when they have choice. Business travelers choose trains over flights for convenience and comfort. Tourists ride the Shinkansen as an experience in itself. The trains became culturally significant rather than just functionally necessary. Environmental benefits that were barely considered in 1964 have become critically important. Climate change requires reducing carbon emissions from transportation, one of the largest sources of greenhouse gases. The Shinkansen proves that long-distance ground transportation can compete successfully with aviation while producing far lower emissions per passenger. As electricity grids shift toward renewable sources, electric trains become even cleaner. The model of fast, frequent, comfortable electric trains connecting city centers offers a path toward sustainable mobility that doesn't require sacrificing speed or convenience. The system shows that infrastructure investment can pay enormous returns when done well. The initial Tokaido Shinkansen cost 380 billion yen, an enormous sum that critics called reckless. Yet that investment generated returns many times its cost through economic growth, reduced congestion, energy savings, environmental benefits, and quality of life improvements. Modern cost-benefit analyses struggle to capture these diffuse benefits, but they are real and substantial. The Shinkansen made Japan more productive and prosperous than it would have been without it. Perhaps most importantly, the Shinkansen stands as proof that ambitious infrastructure projects can succeed. Much of the modern world seems to have lost the ability to build large, complex projects on time and on budget. Construction costs escalate, schedules stretch indefinitely, projects get canceled after wasting billions. The Shinkansen was built in 5 years despite enormous technical challenges, opened on schedule for the 1964 Olympics, and exceeded every performance target. This wasn't luck or unique to 1960s Japan. It resulted from clear goals, competent engineering, adequate funding, and sustained commitment from leadership. Current societies could build equivalents if they chose to. The technology exists. The engineering knowledge is well established. Financial resources are available in wealthy countries. What often lacks is political will, public support, and organizational competence. Projects get delayed by endless reviews, lawsuits, budget fights, and changes in requirements. The Shinkansen succeeded partly because Japan in 1959 could make decisions and execute them without the procedural barriers that now obstruct infrastructure in many democracies. Yet the Shinkansen also shows that technical excellence alone is insufficient. The system works because of cultural factors, the dedication to punctuality, the respect for public goods, the willingness to maintain infrastructure properly, the pride in collective achievements. These cultural elements cannot be easily exported or replicated. Countries that have tried to build high-speed rail with imported Japanese or European technology have often struggled to achieve the same operational excellence. The trains and tracks are necessary but not sufficient. Looking forward, the Shinkansen faces challenges despite its success. Japan's population is aging and declining, reducing the passenger base that funds the system. The most profitable route, Tokyo to Osaka, may face redundancy from the maglev Chuo Shinkansen, though this also provides resilience. Climate change brings more extreme weather that disrupts operations. Earthquake risks remain ever present. The massive debt from constructing later lines continues to burden the operators, yet the Shinkansen seems likely to endure and adapt. The system has survived oil crises, economic recessions, natural disasters, and pandemics. Each challenge has been met with innovation and adaptation. The trains have become faster, quieter, more efficient. The network has expanded to serve more of the country. Operations have become even more reliable. There is no reason to expect this trajectory to reverse. For the rest of the world, the Shinkansen remains a provocation and inspiration. It proves that better transportation is possible, that safety and efficiency can coexist with profitability, that infrastructure can be both functional and excellent. As countries struggle with congestion, emissions, and deteriorating infrastructure, the Japanese bullet train demonstrates that solutions exist. The question is not whether we can build systems like the Shinkansen, but whether we will choose to. 60 years ago, skeptics called the Shinkansen an impossible dream, a reckless gamble that would bankrupt Japanese railways. They were wrong. The bullet train became one of the 20th century's greatest infrastructure achievements, reshaping a nation and inspiring the world. It stands now not as a relic of a bygone era, but as a working model of what we could build if we had the vision and commitment. The Shinkansen is not just a train, it is an argument, rendered in steel and electricity and precision engineering, that we can build a better future if we dare to try.